In the beginning, there is the hush of possibility, a silence so profound it teeters between terror and awe. This is the hush before a curtain rises, the moment before the universe opens its hidden doors. The question hangs in the darkness, luminous with potential. Is this the only universe? Or are there others, shadows, echoes, reflections, undiscovered, perhaps unreachable, yet woven into the very fabric of our existence? Across centuries, the brightest minds have dared to imagine what lies beyond the limits of our cosmos. They have peered past the observable into the unseeable and found there a landscape as rich and strange as any myth. Parallel universes, multiverses, many worlds. These are words that pulse with both scientific rigor and the lyricism of dreams. The journey to understand them is not a straight path, but a spiraling odyssey through mathematics, philosophy, experiment, and imagination. It is a journey that threads through quantum mechanics, cosmology, particle physics, and the deepest mysteries of consciousness. The story is not merely about what is out there, but about what it means to be here, what it means perhaps to be only one among many. Let us begin then at the place where our own universe first revealed its strangeness. It is 1927. In a quiet laboratory in Brussels, the founders of quantum mechanics gather for the Solvay conference. Einstein, Bohr, Heisenberg, Schrödinger. They debate, argue, and marvel as the subatomic world unfolds its secrets. They discover that, at the smallest scales, nature is not deterministic, but probabilistic. A particle is not in one place or another, but in a superposition of possibilities. Only when it is observed does it collapse into a single reality. This is the first crack in the wall, the first hint that reality may be more layered than it seems. Hugh Everett III in 1957 follows the crack to its logical conclusion. He proposes the many worlds interpretation of quantum mechanics. Every time a quantum event occurs, the universe splits, branching into as many worlds as there are possible outcomes. In one, Schrödinger's cat lives. In another, it dies. There is no collapse, only an ever-ramifying tree of realities. Everett's theory is radical, even scandalous. It is ignored, dismissed, and nearly forgotten. But it lingers, like a spectral afterimage, waiting for its time. Meanwhile, cosmologists look up instead of down. They see a universe expanding, cooling, its galaxies receding into the infinite dark. In the 1980s, Alan Guth proposes inflation, a brief, exponential expansion in the early universe, smoothing out its wrinkles and setting the stage for all that follows. But inflation has implications that are as startling as anything in quantum theory. It suggests that our universe is only a bubble in an unending froth, a multiverse of inflating regions, each with its own laws, its own constants, its own fate. This is the Level 1 and Level 2 multiverse, as classified by Max Tegmark. Level 1 is a simple extension. Infinite space means infinite copies of ourselves, somewhere far out beyond the cosmic horizon. Level 2 is more radical. Universes with different physical laws, born from the same inflationary process. Then, in the 1990s and 2000s, string theorists joined the fray. String theory, in its quest to unite gravity with quantum mechanics, predicts not a single universe, but a vast landscape of possible vacua, perhaps 10,500 or more. Each vacuum corresponds to a different way to compactify the extra dimensions of string theory, giving rise to different laws of physics. This is the landscape multiverse, a Level 2 or even Level 3 construction, depending on interpretation. The cosmological constant problem, the fact that our universe's vacuum energy is so improbably small, finds a possible explanation here. Perhaps we live in one universe among many, and only in a rare few does the vacuum energy allow for galaxies, stars, and life. But theories are not enough. Science demands evidence, and so in particle colliders, quantum laboratories, and telescopes peering to the edge of the observable, researchers search for signs of the multiverse. The experiments are subtle, ingenious, sometimes desperate. Some look for deviations in the cosmic microwave background, the afterglow of the Big Bang, that might betray collisions with other universes. In 2010, Stephen Feeney and colleagues analyzed data from the Wilkinson Microwave Anisotropy Probe, searching for circular patterns that could be the scars of such encounters. The evidence is tantalizing, but ambiguous. The search continues with the Planck satellite, ever refining, ever hoping for a sign. Others probe the quantum world for signs of branching realities. The Leggett-Garg inequality, Bell's theorem, and delayed choice experiments test the foundations of quantum mechanics, seeking perhaps a way to distinguish many worlds from hidden variables or collapse theories. But the universe is cagey. It reveals its secrets only in riddles. So far, no experiment has definitively favored the many worlds over its rivals. Yet the theory's logical coherence and its ability to explain quantum paradoxes without ad hoc mechanisms continues to attract adherents. String theorists, for their part, seek indirect confirmation. They search for supersymmetry at the Large Hadron Collider, for signs of extra dimensions in high-energy collisions, for patterns in the cosmic microwave background that might betray the shape of higher-dimensional space. The results are frustratingly null. No supersymmetric particles, no extra dimensions, no smoking gun. Yet the mathematical beauty of string theory, its power to unify forces and particles, is undeniable. There are more exotic searches still. At the South Pole, the IceCube Neutrino Observatory waits for high-energy particles from the farthest reaches of the cosmos. Some theorists speculate that neutrinos might tunnel between branes, higher-dimensional surfaces in string theory, hinting at parallel universes just out of reach. In 2020, reports of anomalous neutrino detections stir excitement, but further analysis suggests more mundane explanations. The mystery remains, tantalizing but unresolved. In the realm of mathematics and philosophy, the debate is fiercer still. Max Tegmark proposes his own radical vision, the mathematical universe hypothesis. Reality is not merely described by mathematics. It is mathematics. Every consistent mathematical structure exists as a universe. Ours is but one among an infinite ensemble, each as real as the next. This is the level-4 multiverse, the most extravagant of all. Critics object that this is metaphysics, not physics, but Tegmark counters that the border is more porous than it seems. What then has been found? The answer is both much and little. There is no smoking gun, no incontrovertible proof that parallel universes exist. Yet the theories that predict them, quantum mechanics, inflation, string theory, are among the most successful in science. They explain what we see, even as they point beyond it. The multiverse remains a plausible, perhaps necessary, consequence of our best understanding of nature. And what mysteries might these parallel universes explain? The list is long and profound. The fine-tuning of the physical constants, the fact that gravity, electromagnetism, and the nuclear forces are balanced just so, allowing for stars, chemistry, and life, is one of the deepest puzzles in cosmology. If there are many universes with many sets of constants, then it is no surprise that we find ourselves in one that allows for observers. This is the Anthropic principle, controversial but potent. The problem of quantum measurement, the question of why observation produces a single outcome when the equations allow for many, is resolved in the many worlds picture. All outcomes happen, but in different branches of reality. There is no need for mysterious collapses or hidden variables. The mystery is revealed as a consequence of our limited perspective. The cosmological constant problem, which has bedeviled physicists for decades, finds a possible solution in the landscape multiverse. If there are many vacua, with many values of the vacuum energy, then it is no surprise that we find ourselves in one that is small enough to allow galaxies to form. The mystery is not why the constant is small, but why we are here to ask the question. The answer, perhaps, is selection among infinities. Yet for all these explanatory successes, the multiverse remains on the boundary between science and speculation. The critics are fierce. Some argue that a theory that predicts everything predicts nothing, that the multiverse is unfalsifiable and thus unscientific. Others counter that indirect evidence, logical necessity, and mathematical beauty are themselves forms of confirmation. The debate is unresolved and perhaps unresolvable. There are other, more speculative lines of inquiry. In the strange territory of quantum gravity, theorists propose that black holes may be portals to other universes. The information paradox, the firewall hypothesis, and the holographic principle all suggest that the interior of a black hole may be more than it seems. In 2014, Stephen Hawking proposes that information may escape from black holes, not into our universe, but into parallel ones. The mathematics is subtle, the observations impossible, but the idea lingers, a whisper from the edge of knowledge. There are even hints in the mathematics of quantum entanglement that space-time itself may be an emergent phenomenon. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that entangled particles are connected by microscopic wormholes, Einstein-Rosen bridges, across space-time. If this is true, then the fabric of reality is stitched together by connections that transcend the ordinary boundaries of space and time. Perhaps in some unfathomable sense, every entangled system is a bridge between worlds. In the laboratory, the search continues. The Large Hadron Collider, the world's most powerful particle accelerator, smashes protons together at energies of 13 TeV and higher. Physicists search for miniature black holes, for deviations in gravitational force at sub-millimeter scales, for rare decays that might betray the presence of hidden dimensions. Each null result is both a disappointment and a clue. A tightening of the web, a narrowing of the possible. Astronomers, too, scan the skies for evidence. The cosmic microwave background, mapped in exquisite detail by Kobe, W-Map, and Planck, is the afterglow of the Big Bang, a snapshot of the universe when it was 380,000 years old. Subtle anomalies in its temperature and polarization may hint at collisions with other universes, or at the imprint of higher dimensional physics. The search is painstaking, statistical, and fraught with uncertainty. Yet each new map is a window onto the possible. In the quantum realm, experiments in quantum computing may offer new insights. If the many worlds interpretation is correct, then quantum computers may be exploiting parallel universes to perform calculations that are impossible in a single world. David Deutsch, the pioneer of quantum computation, has argued that the power of quantum algorithms is evidence for many worlds. The debate is ongoing, the experiments subtle, the conclusions elusive. The story is not only one of theories and experiments, but of people, of the men and women who have dared to dream of other worlds. Hugh Everett, dismissed in his own time, dying young and obscure, is now recognized as a visionary. Bryce DeWitt, who championed many worlds, suffered professional ostracism. Max Tegmark, eternal optimist, embraces the mathematical multiverse with enthusiasm. Alan Guth, father of inflation, marvels at the implications of his own theory. The story is human, as well as cosmic. There are moments of despair and moments of wonder. The multiverse, if it exists, is both exhilarating and humbling. It offers a solution to the deepest mysteries of physics, but at the price of our uniqueness. If there are infinite copies of ourselves, living out every possible life, what becomes of meaning, of choice, of purpose? Philosophers and theologians grapple with these questions, weaving new tapestries of sense and value. Yet for all its strangeness, the multiverse is perhaps no stranger than the universe we already know. Quantum mechanics, with its superpositions and entanglements, relativity, with its warping of space and time, the Big Bang, with its creation of everything from nothing, all are as counterintuitive as any multiverse. The wonder is not that the universe is strange, but that we are capable of glimpsing its strangeness. The search for parallel universes is, in the end, a search for ourselves. It is the search for meaning in a cosmos that is vaster, stranger, and more beautiful than we can imagine. It is the recognition that our own existence is both improbable and inevitable, that we are, in some sense, the universe looking at itself, across an infinite sea of possibilities. Let us return then to the laboratory, to the telescope, to the blackboard thick with equations. The search continues day after day, year after year. New experiments are planned. The next generation of particle colliders, capable of probing ever higher energies. New telescopes, sensitive to the faintest whispers from the edge of the observable. New quantum devices, able to test the most delicate predictions of theory. Each advance is a step into the unknown, a widening of the horizon. There are dreams of even more audacious experiments. Some theorists propose using entangled particles to send signals into parallel universes, or to detect the gravitational influence of hidden dimensions. These proposals are, for now, more science fiction than science, but so, once, were black holes, quantum computers, and the accelerating universe. In the meantime, the multiverse provides a framework for understanding. It explains the fine-tuning of the constants, the mystery of quantum measurement, the vastness of the cosmic landscape. It offers hope that the deepest puzzles of physics may one day be solved, not by reducing the universe to a single equation, but by embracing its multiplicity. Yet the story is not finished. The evidence is ambiguous, the theories incomplete. The multiverse remains a frontier, a place where science meets philosophy, where calculation meets imagination, where the known meets the unknown. It is a place of danger and of promise, of confusion and of clarity. Let us pause then and reflect. What does it mean to live in a universe that is one among many? What does it mean to be a person, a consciousness, a story, in a cosmos of infinite stories? The questions are profound, the answers tentative. Perhaps the greatest lesson of the search for parallel universes is humility, the recognition that our own perspective is limited, our own knowledge partial, our own existence both unique and universal. Yet there is also wonder. The multiverse, if it exists, is a testament to the power of the human mind, a mind capable of imagining realities beyond the limits of observation, of weaving together mathematics, experiment, and intuition into a tapestry of possibility. It is a testament to the unity of knowledge, to the idea that the deepest questions are also the most beautiful. The search for parallel universes is, in some sense, the search for the limits of science itself. It is the attempt to ask questions that may never be answered, to explore regions of reality that may forever be beyond our reach. It is the recognition that the universe is not a closed book, but an open story, a story that we are privileged to read and perhaps to write. As we look back over the history of the quest, we see a pattern. Each time science has expanded its vision, it has revealed new realms of reality. The solar system gave way to the galaxy to the universe perhaps to the multiverse. Each expansion has brought new questions, new mysteries, new possibilities. There is perhaps no end to the adventure. The universe is not only stranger than we imagine, but stranger than we can imagine. The search for parallel universes is a reminder that the cosmos is a place of infinite wonder, a place where every answer gives rise to new questions, where every discovery opens new doors. In the end, the journey is its own reward. The search for parallel universes is a journey into the unknown, a journey that challenges our assumptions, expands our horizons, and deepens our sense of wonder. It is a journey that unites science and philosophy, reason and imagination, fact and possibility. Perhaps somewhere in a parallel universe, another version of you is reading these words, marveling at the same mysteries, pondering the same questions, dreaming the same dreams. Or perhaps not. The answer, for now, remains just out of reach. A whisper on the edge of possibility, a glimmer in the darkness, a promise of worlds yet to be discovered. In the silence that follows, the hush of possibility returns. The curtain has not fallen. The story is not finished. The search continues, and with it the hope that one day we may find the answers we seek, not only to the mysteries of the multiverse, but to the deeper mystery of our own existence. For in every question there is a world, and in every world a question, waiting for the light of discovery.